I'm going to do is give you a little bit more information about swim bladders and then set you up to do an activity that'll count for some lab points. Here's a picture from one of the previous PowerPoints that shows you the split, remember, from the ancestral simple air sac lung between eventually the tetrapods or the sarcopterygians and the ray fin fish, which are on the right side. And the ray fin fish have developed these swim bladders that help them control their buoyancy. Here are a couple pictures of swim bladders. So to the left, you see it's marked air bladder, the same thing. Right up against the spine, you see this transparent, basically, bubble that's just up against the spine. So it's kind of dorsal to most of the rest of the organs there. And then in the anatomy drawing, you can see the location of it. And if you look at the little pullout from the anatomy drawing, you can see that in most ocean-going fish or fish that are in deep water, it's actually completely disconnected from the pharynx. So unlike the lung, it no longer has a connection to the mouth in most ocean-going fish. And it's essentially exchanging gases with the respiratory system. So there's the gas exchangers to bring gas in and out of the swim bladder, so it can change the actual amount of gas in that swim bladder, which is a really important feature and a very sophisticated organ. In many ways, in some ways, it's somewhat more sophisticated than the lung. Recall that sharks branch off before the development of that primitive lung from which both swim bladders in ray fin fish and lungs in tetrapods evolved, and so they don't have the ancestral organ that would have become either a lung or a swim bladder, so they don't have swim bladders at all. But of course, they're excellent swimmers, and obviously the shark body plan must work pretty well because they've been around for a long time and it hasn't changed very much. So natural selection hasn't been, deciding that there's a better body plan for sharks, and so it must work pretty well. They swim well because of a couple of different adaptations. One, they have a light cartilaginous skeleton, and remember that's a little bit confusing because you see in the phylogeny that they're descended from something with a mineralized skeleton, and it used to be thought that they came before that point, but now it turns out that it looks like they have descended from something with a heavier skeleton to this lighter skeleton again. And the other adaptation they have is a large liver in many of the fast swimming sharks that produces this low density oil to again make them lighter. Even with these features, sharks are slightly heavier than water, and therefore they need to generate an upward force as they move, or they're going to sink to the bottom. So they're sort of beautifully proportioned to work in a way similar to an airplane. As they move forward, some of their forward motion is converted into a lifting force. You can see a picture from a study on the right without having to go into the details of that, but basically it looks a lot like kind of an engineer's analysis of an airplane with lifting forces and the weight of the shark and the attitude of the shark and so forth. That feature of a shark has advantages and disadvantages. They're terrific swimmers. They're very fast. They can change depth rapidly, but they have to keep moving forward or they'll sink, and they cannot swim backwards. So if you ever watch a little fish in an aquarium, it has that over a shark, in that it can actually hold its position in the water column without moving forward at all, and it can also even swim backwards. So let's talk about buoyancy a little bit. Buoyancy refers to whether an item is going to float or sink or not, right? So you see three types of buoyancy here, pretty much straightforward. Sharks are basically a little bit negatively buoyant, which means that they'll sink unless they do something about it, right? Obviously, if you're neutrally buoyant, then you're the same density as water, and you don't really have to put any work into maintaining a lift force. Or if you're positively buoyant, you're going to float to the top, which isn't great if you're most fish anyway. Most fish want to be down in the water column. So why not just have a body plan that is completely neutrally buoyant? Well, the problem with that is that the density of water varies. And so depending on salinity and temperature, the density of water can vary. And so fish can't really pick one neutral buoyancy. Another thing that's going to be important for us to understand is that fluids like water in the ocean and like the fluids in a shark, as well as the rest of the shark itself, are relatively uncompressible. Water is very uncompressible. It takes a tremendous amount of pressure to change any volume of water at all. Try filling up a syringe completely and capping it off with water and then compressing that syringe, and you won't be able to do it. Whereas gas is very compressible. So if you take the same syringe and fill it up and plug the end and push the plunger, you'll be able to compress that. And so if you look at the two cross sections that I've conceptualized with those ovals there, basically think of the shark as kind of solid and fluid, and so completely uncompressible, relatively speaking, for all practical purposes. And ray fin fish, of course, have this big air bladder in there, and that is compressible. The two biggest factors that affect then the density of water are temperature and salinity. Because water is uncompressible, pressure doesn't really have any effect on its density. So temperature and salinity are things that the fish has to deal with, affecting the density of the water and therefore affecting its buoyancy. So as a fish is going to move through the water, it's going to experience changes in temperature and salinity. That's going to affect the density of the water and therefore the relative buoyancy of the fish. Ray fin fishes can manipulate their gas in the swim bladder and therefore remain neutrally buoyant. Sharks don't do this, can't do this, but they, of course, just overcome that with just by swimming. So they expend energy to overcome the sinking. As fish move through the water, they're going to experience a change in pressure as well. So at the surface of the ocean, just below the surface, the pressure is basically 1 atmosphere. That's about 100 pascals. And for every 10 meters of depth, the pressure is going to increase by another atmosphere or 100 pascals. And so the deeper you go, the more pressure, as you perhaps are aware. That's not going to affect the density of water because remember, it's not compressible. But as a fish with a swim bladder dives, the gas in the swim bladder is going to compress. So the same amount of gas is going to take up less space when it's under more pressure. Like if you pressurize, if you take that syringe that we talked about in the previous slide, plug the end of it and fill it with gas, pressurize it, and you're going to be able to make it take up less space. Well, the same thing is going to happen as the fish goes deeper into the ocean. For an activity then to kind of help us understand some of the things that we just talked about in terms of how swim bladders work and how fish experience buoyancy in the ocean, we're going to make a kind of a science toy that's kind of a fun one to work with, called a Cartesian diver. And the Cartesian diver, basically what you need are a soda bottle, a 2-liter soda bottle, or any soft bottle with a tight top that you can fill up with water, and it should be clear so you can see what's going on inside. And then you're going to essentially make a little float that is just barely above the density of water, so it'll just barely break the surface. There are all kinds of different ways to make one. I could give you one specific way to make one, but it's probably better if you go look around the internet a little bit, because you may have some things in your house that'll work well. And I'll give you some options too, but let me just kind of give you the broad overview on this slide, and then we'll go into more specifics. So there's a lot of different ways to make one, but basically what you want is a float that has an air bubble in it, and that air bubble can be compressed if there's pressure on it. So if it's a sealed float with squishable sides, that'll work. So things like a cell from, or a couple of cells from a sheet of bubble wrap, or you just take a little corner of a plastic bag and tie it up tight so it makes a little balloon. The other possibility is you can have a float with an open bottom that can trap a bubble. One that works reasonably well is if you have like a felt tip pen cap. You have to make sure the cap doesn't have holes in the top. A lot of ballpoint pen caps have air holes in the top, but what you want is kind of a little bell that you can trap a bubble in. So if you hang weights off of it, the open side will be down and the bubble will be in there, and then pressure can get at the bubble, because even though the sides of the cap are rigid, since it's open, the pressure will push on the bubble from just the open part. And then you're going to need some weights to hang off your float. And so you can use whatever you can think of. Some wire, paper clips are good, washers, whatever kind of weight you can attach to your float. And as I said, probably the best thing to do is look around a little bit and see what you have and how it matches up with all the different procedures that are out there. The next thing you're going to do is essentially take that float and weight and make adjustments by adding more weight until it just barely floats. Of course, that's a little bit challenging because at some point you're going to add weight and it's going to sink. And then what you can do is, if you're using paper clips, for example, you can maybe snip a little bit of wire off the paper clip to make it just a little bit lighter. Just get it as close to just barely floating as you can. You have some leeway, and once you set it up, you'll see whether you did it well enough. And if you didn't, then you're going to just have to go and readjust it. So it's helpful not to do this in the bottle, but to do this in like a sink or a big pot or something. And you want to probably do this in your kitchen where you can get things a little bit wet. So then you got to get the diver in the bottle. If there are a couple different ways to do this. If it's a sealed float, well, then you can just kind of plop it in the bottle, so that's a little bit easier. If it's one that's trapping a bubble like a pen cap, you can take the bottle and fill it all the way up with water while your float is in your your test pot or whatever. Turn the bottle over with the water into your test pot, and then submerge your float underneath the bottle and squeeze the sides of the bottle, put the float up and suck it in, and that way you can get in the bottle that way, and then flip it and cap it. Once you've got it in the bottle, make sure it's filled all the way to the top, because any air in there is just air you have to compress, and you don't want to have to compress air. You're going to compress the sides of the bottle, and that will result in the bubble compressing and make your diver dive. So how to make your diver dive? Squeeze the bottle, and you should be able to make the diver sink. Don't be afraid to squeeze pretty hard if you need to. The closer your diver is to the density of the water, the less you'll need to squeeze. So depending on how good you got it adjusted before you put it in, you might make it a little bit easier. But if you can't squeeze it hard enough, then you might just have to readjust your float a little bit and try again. This is a Cartesian diver, and this little contraption let me just demonstrate it first, and then we'll talk about why it works and how we can do something with it that's related to swim bladders. Here's my little tinfoil fish, and this is a little pen cap. The pen cap has a bubble trapped in it. This is a 2-liter soda bottle, and I've adjusted the weight of the 2-liter soda bottle, of the pen cap and the fish, so that it just barely floats. Now the soda bottle is completely full of water. If I compress the sides of the soda bottle, you'll see my little fish sink. And if I let it relax, it'll come back to the surface again. So, in fact, if I'm really careful about it, I can get them to just kind of hover like that. And so that thing is called the Cartesian diver, and you're going to have a chance to make one of those, and I'm going to explain a little bit how it works. So what happened when we compressed the size of the bottle there? Something obviously happened because the fish sank, right? So when we compress the size of the bottle, well, let's think about the components of the whole system. First off, mostly it's filled with water, and we learned that water doesn't compress. It's going to basically not change when you put pressure on the side. So something's got to give. The only thing in there that's going to give is that air bubble. So when you push on the sides of the bottle, the thing that you're really compressing is the air in that air bubble. It's the same amount of air, but the volume of it is going to change because you've pressurized it. When the air bubble compresses, well, what's going to happen next? Well, if we think about it, the air is really the only thing in there that's lighter than water. And so when that air bubble compresses, the buoyancy of that whole pen cap and fish and air bubble is going to be less because now there's less air to hold the thing afloat. So the next thing that's going to happen is, well, probably going to sink, right? So the sequence of events then is you've got this fish with the air bubble floating at the top of the bottle. You compress the sides of the bottle, and the only thing I can give is the air in the pen cap. It compresses, same amount of molecules of air in there, but compressed together, so pressurized, and that changes the buoyancy, and the fish sinks. This should look a lot like the description of what happens to a fish when it goes down in depth that we saw in slide 8. So take a look at slide 8 again and compare it to this figure, and I think you'll see the similarities. Now, the thing that a fish can do that my little faint fish can't do is that if the fish starts to sink against its will and it wants to sort of rise again in the water column, it can actually add some air to that bubble. So if it goes down to deeper water where the pressure is higher, it may need to add some air to maintain neutral buoyancy. Even if the salinity and temperature and everything is the same, the density of the water hasn't changed, but the pressure on the fish has changed, and so the amount of air it needs to maintain that volume in the air bladder has gone up. So it's going to need to manipulate the amount of air in that air bladder, which my fish can't do. If I don't put any pressure on the bottle, that simulates the fish swimming at shallow depth, right near the surface. If I put lots of pressure on the bottle, that's kind of like the fish is down in the deep ocean. Remember, my fish can't do anything about the amount of gas molecules in its swim bladder, so it's kind of unable to control its own buoyancy. But remember, I could kind of pressurize the bottle just enough so it would float, kind of hover in the middle of the bottle, and that depth is essentially, or that amount of pressure is analogous to the depth for which that fish would have its swim bladder correctly set for. It's kind of like a broken clock that's right twice a day. That fish can't control its depth settings, so it can't control how much gas is in its swim bladder, but it works for one depth. If I was really industrious, I'd make a bunch of fish that were slightly different, and then as I pressurized the bottle, one after the other would kind of drop down, and you'd see that different amounts of buoyancy would be appropriate for different depths.